Hello everyone, my name is Melissa.L.C and I'm presenting my spatial analysis final project. My research question was whether ArcGIS Pro can identify specific locations within a small property for installing water retention mechanisms in a degraded arid landscape. The goal was to use hydrological spatial analysis toolsets to identify the sub-watersheds within a specific boundary. A rancher in San Blas, Mexico, offered up his land as the designated pilot site for this project, and the objective is to use these results to prepare his land for future regenerative farming and ecosystem restoration endeavors. For some context, today arid landscapes account for approximately 45% of the world's terrestrial cover. They also offer the most potential to increase land arability and microclimate buffers. However, these arid drylands are of high ecological vulnerability due to their sparse vegetative state and erratic rainstorms, which makes the soil more susceptible to degradation. Mexico is one of many countries experiencing widespread drought and has become more prevalent over the last 2 decades. This is leading to disruption of hydrologic cycles, the climate, and groundwater retention and water availability. Despite these effects, many ranchers, pastoralists, and farmers continue non-sustainable practices like overgrazing, land clearing, and monoculture due to socioeconomic factors and lack of environmental education. Current research shows that watershed analysis is crucial for understanding groundwater recharge and soil conditions, which influence water storage through infiltration and percolation. The traditional methods of analyzing geomorphology, though important, are labor-intensive and impractical for large-scale applications. So as a result, geospatial information systems and remote sensing have become essential tools for assessing watersheds using parameters like evaluation and slope, which help us understand the soil structure, the erosion, and water flow. Effective water catchment and groundwater recharge are particularly vital in drought-prone areas like Baja, Mexico. Current spatial analysis techniques continue to evolve, with GIS and remote sensing offering a more accurate insight into watershed health despite these data limitations. After finding the most current digital elevation model possible for this region of Mexico, I was able to start experimenting with watershed creation workflows. Here you can see the most successful version of a model builder after much trial and error, which I will discuss shortly. The beginning of the analysis was marked with a lot of frustration due to inconsistencies with elevation, the outdated land cover maps, and issues converting geo-coordinate systems to projected systems, which produce substandard results. These are seen on the next slide. The methodologies here consisted of making a flow accumulation output for identifying the parent watershed, followed by a topographic map to create the watersheds. This approach generated 2 topo to raster DEMs, one with a geographic coordinate system and the other with a projected coordinate system to create the water flow network. However, the outputs for both rasters were significantly different, with elevations that did not match each other. As a result, these topo to raster maps were not considered for further analysis. The biggest step that made a difference was using a projected digital elevation model instead of the geographic coordinate system, then making sure to fill sinks in the flow accumulation raster. These 2 adjustments laid a clear foundation for delineating and identifying the watersheds for all scales. The key to finding the preferred size of the watershed was found by changing the symbology of the flow accumulation output. The first image in black is the successful version of the flow accumulation tool that allowed me to create a parent watershed large enough to encompass the whole area of interest and the 2 mountain ridges. I wanted this large enough so that I could get a sense of where the water was flowing from in all directions of the immediate landscape. This tool required testing out different thresholds with the raster calculator, and it also required using a projected coordinate system filled sink flow accumulation layer as the input. As you can see here in the gray images, as the thresholds get smaller, there's more flow accumulation channels that are visible. This was useful for validating the stream to feature tool output layer, as well as helping get some sense of primary areas of water flow and areas with less water accumulation. And you can see here that using a stretched symbology is ideal for the larger watersheds. And in the image with the blue watershed, this is the watershed I ended up going with for this project. I chose a pour point well outside of the property boundaries. And if you see here in the purple, when I chose this is the flow accumulation cell that I had chosen here, and it didn't cover everything. So again, we used the blue parent watershed for this project. For smaller watersheds, I used a discrete symbology. This allows you to see more variation in water flow, and it can create smaller individual polygon layers. Using the smooth polygon tool, this gives them a more realistic shape for aesthetic reasons. Once they are all smooth, you can go ahead and clip the stream to feature to the polygons. Once these steps are done, all you need to do is create separate shapefiles to add your pour points to, and use those pour point shapefiles and desired flow accumulation as inputs for the watershed tool. Here is an example of what this looks like when all put together. To assess where water will flow within the smaller watersheds, you can then go ahead and use the raster calculator tool that creates a nice representation of water flow connectivity. This will be used to create the stream to feature layer. Here, as you can see, it's these white lines going through each polygon. And this layer is a great way to represent water flow in a more visual manner that can be easily interpreted by a client. Then you will create a stream to feature layer and clip that layer to each individual watershed. You don't need to do this, but I found it easier to analyze it than having a whole screen filled with stream flow lines, as you can see in the top left. Creating a contour layer was also performed. These contours were useful because they allow us to understand how quickly water will flow over the landscape, where water has more chances to percolate into the soil, and spot potential areas of degradation. The landscape elevations often determines what kind of water retention mechanisms are appropriate. Okay, results. The objective of this analysis was to gain an understanding of the parameters needed and an accurate methodology to analyze drylands in need of water retention using the GIS applications. These applications will help land managers and local stakeholders make informed decisions on how to improve water retention with water flow that come through their watershed and how to recharge groundwater to restore ecological function and revegetate these drylands on both small and large scale. The results of this analysis were satisfactory in identifying sub-watersheds within a specific boundary. These processes allowed me to identify where sub-watersheds on the property became too steep on the mountain slope, which is to the left of the river. If you look at both images, you can see that I took away about half of the watersheds on the top upper left. So the image on the right is the area that is of the most concern at the moment. New watersheds can be added once the stakeholder confirms accessibility and interest in installing water diversion mechanisms or catchments higher up the mountain. The goal is to divert water flow to the main property where the rancher does have cattle grazing, and also his farm. So instead of allowing it to flow into the river, the water can be diverted into areas of most need. This is another way we can present information about a specific watershed catchment. I like this map view because we can see where the stakeholder's home is as well as the areas that are most degraded. The stream to feature layer clipped into this polygon gives a great representation of how and where the water is flowing into the center of the catchment, giving us a better idea of where we want to divert water flow to the areas of highest concern. The current data used for watershed delineation is generally satisfactory. but there is some uncertainty due to the lack of high temporal, spectral, and spatial resolution data, as well as the need for more water flow verification. Stakeholders should validate the geocoordinates of the watershed polygons to ensure accuracy as well. Additionally, the existing land cover land use data that I procured for this spatial analysis was outdated and lacks higher resolution, necessitating the creation of accurate land cover maps using ground data and remote sensing, along with recent NDVI differencing maps to highlight the significant spectral changes. Despite the presence of broadleaf trees and shrubs, the land in this region of Mexico is severely degraded, with soil struggling to retain water due to sparse vegetation, compaction, aridity, and temperature, and uneven terrain. So the stakeholders have provided input on preferred grazing areas and natural water retention landscapes, but creating a suitability map using land cover data alone is not yet feasible due to these constraints. Here are the next steps to improve these results for creating a usable map for creating a water retention landscape. After extensive research, I found that it would be beneficial to incorporate more morphometric analysis parameters for this watershed analysis. These include stream number, stream frequency, stream order, stream length, drainage density, infiltration number, and relief. The current project analysis will lay the path for the next phase where more data will be collected to create suitability maps with parameters that include land cover assessment using updated land cover land use maps as a weighted overlay, also soil tape data, NDVI differencing, and other remote sensing applications. The finished project, phase 3, will lead to a replicable model that can be applied on a larger scale to be used in the Baja Sur region. Ground truth data collection for supplemental validation will be the last step for creating an accurate suitability model. And here is my works cited page if you'd like to learn more about the background research and techniques. This concludes my presentation, and I appreciate you listening and hope you found these methodologies useful for your future GIS projects.